All right, welcome everyone. We're going to discuss some of these properties for integrals and introduce indefinite integrals as well. Okay, so let's start to share the screen with DocCam and we'll get going on these properties and this process. All right, here we go. So let's look at some of these properties, okay? And so recall that we had talked about and hope we got some practice with these definite integrals, right? The integral from a to b of some function f of x dx, right? Whatever variable we're depending on. I'll probably have f of t dt, f of theta d theta, right? That variable and this integrating factor, I call it dx, right? Should match. And when we look at those integrals, this represents for us the area under, right, or between that graph, that curve, f of x, over the interval from a to b, okay? And so that's how we're understanding geometrically what that definite integral represents for us. So if we have our function, my typical little curve here, we have our interval, a to b, and that integral represents this amount of area, or the net area, in case our graph happens to go below the x-axis, this negative area, okay? But that's what this integral represents for us. And the process of integration is finding that area for us. We talked about the limit definition, okay? And so some of these properties of our definite integral, some statements we want to make sure we identify is that we look at these cases of graphing, okay? So properties of the definite integral. And some of those actions we're going to use to compute, okay? But first up, if we have this integral with the same upper and lower limits of integration, right? In this case, we're looking for the area over a single point. That's going to be equal to 0, right? We can't contain any area under a point. So when we have the same upper and lower limits, that interval is going to go to 0. And we can see this in the calculation discussion later as well. And then this next property, that when we look at this integral from a to b of f(x) dx, and so again, most commonly when we do our limits of integration, we're expecting those limits to go from least to greatest, right? From left to right on our x-axis here, on our coordinate system. But what if we switch the order of those limits of integration? So in this case, I kind of represent like now I'm trying to accumulate this area, working backwards, starting down here at b and then adding up. Well, if we kind of work backwards, that means that all of our values are going to be the opposite, going the opposite direction. So we're going to get that negative. And so when we start to see if we might need to change those limits of integration, change the order, we can do so. But whenever you flip, whenever you change the order of integration, the order of your limits, that negative shows up. Okay. So like, for example, if I was to take this integral from 5 to negative 2 of our f of x dx, but that will be x squared dx, right? If I wanted to kind of say, well, this looks more appropriate if I instead went from negative 2 to 5, or from least to greatest, right? We're still dealing with our same function, a little integrating factor dx, but once I change the order of my limits, the negative shows up. Okay. All right. And then kind of getting into our calculation, maybe not necessarily a property, but doing this work. Okay. If I want to actually compute that, remember we're going to do that capital f of x could be to a, or capital F of b minus f of a, right? Where f of x is the antiderivative of lowercase f of x. If I take the derivative of capital F of x, I get that f of x in our integral. Okay. And it always starts off with that subtraction. And so now this brings up an important property, some discussion here, even tied into some of these limits, right? So in this setup of our integral, this f of x must be defined in more strict terms, continuous, but I'm not going to be writing that, okay? It must be defined and not have vertical asymptotes. That's really what we're kind of looking out for along that interval from A to B. Otherwise, we can't compute. Okay, and so for example, even though we might be able to recognize an antiderivative, we can go through these calculations. When I look at this problem from, let's say, let's go from a negative 2 to 5 of this function, 1 over x squared dx, right? So in this case, my f of x, 1 over x squared. And if we think about this graph, notice f of x is undefined when x equals 0. We're going to get a vertical asymptote. And then when we start to graph, right, from negative 2 to positive 5, I know my scaling is a little bit off, okay? What we're going to graph? We're going to graph here. This is at negative 2, 1/4. We can start our way up, but as we get closer and closer to 0, we're going to get this vertical asymptote. Likewise, as we work our way through, this is going to go down, 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 and we're going to end here at this point at 5, 1/25, right? 1 over 5 squared, 1 over 125, 1 over 25. And so as we start to look at this integral, over here, not too bad, not too bad. Even on this side, not too bad. But what about that area where f of x goes to infinity? Right, these huge values. And again, it's not even defined. So we're not really kind of trapping the area. What can we do there? So even though we might be able to use our power rule, we might be able to compute, we can find an antiderivative. Right, we can find that antiderivative for this 1 over x squared, right? Because that's the same thing as x to the negative 2. So our antiderivative, x to the negative 2 plus 1 divided by negative 2 plus 1, which is x to negative 1 over negative 1, or negative 1 over x, right? We can find this value. We can find values at our two limits of integration. Right? But these values, results, will not give us the true solution, since my original function that we're trying to find, that area below, is not defined, right? Has that vertical asymptote in that interval, from negative 2 to positive 5. So even though we can go to that work, we have to double check that, okay, for this graph, for this function, in that interval, we're well defined. If I had changed it, if I had gone up instead from like positive 2 to positive 5, then we're good. We can calculate there and evaluate, get that area, certainly, even back here from negative 2 to negative 1, from negative 2 to negative 1/5, as long as I don't use that 0 where we're undefined, we can actually evaluate using this antiderivative and everything else, okay? So some components to watch out for as we're managing, dealing with those definite intervals, okay? So now let's start to introduce the next topic, all right? So now we're going to start to look at indefinite intervals. So now what these indefinite intervals look like, they're the integral of some function f of x dx. And again, notice there's no limits of integration. There's no values on that integration symbol. There's no values, no numbers to plug in and evaluate. So with these problems, what we're going to find is that our solution is going to be our most general antiderivative. Okay, it's going to be that capital F of x, the antiderivative. And remember, we had done with our antiderivative work before, we had got plus c. We're always going to include this constant of integration. With our definite integral, we leave that off, and even if we did include it, once we do that difference, that subtraction, f of a minus f of b, the constant with that subtraction is going to cancel out anyways. So that's why we kind of leave it off. But now when we don't have limits of integration, we want to use that most general antiderivative. Okay. And so now in that work, right, we're going to need some of our differentiation rules, our integration rules for finding some of these simple integrals, okay, antiderivatives. All right. And so remember, with our derivatives, taking the derivative d dx of a constant, 0. d dx of our x to the first power was 1. d dx x squared was 2x to the first. Slide this up a little bit. We had our general power rule, x to the nth power, n times x to the n minus 1. Before I forget it, the exponential, derivative of exponential is e to the x. The derivative of the natural log, 1 over x. Right, in the textbook, they have that explanation. And then all of our different trig functions, right? dx of sine x is the cosine of x. And I ran out of space to include 1. Okay? But now, let's think of our anti-derivatives. Well, we're going to start to talk about our integrals. Okay, and in the textbook, in the front cover, back cover, you'll see these integral tables and differentiation tables. So they identify these rules. So that way when we start to see some of these more complex functions in the future, they show what that integral, that antiderivative should look like to either shorten some of our work, some of our processes, and or double check, of course, in that discussion, right? And so then when we start to work on it, when we start to see the integral of a constant, we're going to get that constant times x. But then, of course, out of habit, later we'll talk about up here, we're going to need to add some extra constant, right? So I put this plus k. There's my constant of integration. I'll use a different letter just to make it stand out, right? But as we start to go through, the integral of x, 1/2 x squared. I'll put a little plus c. Okay? And now, more generally, I'm going to put x to a power p, and that could be any power. A negative power, a fraction power, square root, right? X to the 1/2 power, x to the negative 1/2 power, 2/3, whatever it might be. It can be any power. When we see that power rule, I'll reverse. 1 over p plus 1 times x to the p plus 1. We add 1 to that power, divide by the new power, and plus c. And this is going to work for any p not equal to negative 1, right? Because what if that power, that exponent is negative 1? Negative 1 plus 1 makes 0. 1 over 0, we can't divide by 0. So then that's going to force us to think back over here to some of those differentiation rules. When we have that x to negative 1, or more commonly 1 over x, that's going to be equal to the natural log. And something that I'll let your next instructor be more cautious and informative about, we're going to use this absolute value bar for x. Okay, and then plus c on the outside. But importantly, the antiderivative of 1 over x is the natural log of x. We incorporate that absolute value because the natural log is only defined for x greater than 0 positive, so we want to make sure that value stays positive. Okay, and then antiderivative of e dx is e dx, of course, plus c outside. And then some of our trig functions, the antiderivative of cosine x dx, sine of x, plus c over here. And then the one I want to bring in as well, the antiderivative of the sine of x. The derivative of cosine is negative sine. So remember this one, we get a negative cosine x plus c, sorry. And then one more, the antiderivative of the secant squared x dx, right? Just remembering some of our derivative rules. The antiderivative of secant squared, tangent, right? What function has derivative equal to secant squared? That's the tangent. So with some of these rules, that power rule, right? These components going in the reverse, getting these antiderivatives are now these indefinite integrals. Okay? So when we're looking at problems, evaluating these integrals, we have to be careful. Are we dealing with a definite integral where we have solid limits of integration? If so, we find our antiderivative and do that subtraction. We get a real number of value as a result, a specific quantity for this area. That's for a definite integral. For indefinite integrals, there's no limits of integration. Our answer is just going to be this most general antiderivative. We're going to have variables, we're going to have an expression, and we can always check. If I take the derivative of my answer, I should get back that original integrand, what we call that function inside the integrand, that function inside. Okay? So there's always a way of double checking these indefinite integrals. Even the definite, you find your antiderivative, take your derivative, make sure it matches up, then compute. Okay? But let's look at this example. Let's evaluate the indefinite integral. Other problems will just say evaluate the integral, and we have to check on our own. Is it a definite integral, indefinite integral? Okay. What if I want to integrate here? This expression. Let's say we have, you know, I'm borrow one from the book, I guess. Let's check out here. Let's check out number 10, page 409. There we go. And this one we have the square root of t times t squared plus 3t plus 2 dt. No limit of integration. We have this expression. And so one thing, when we look at those integration, those rules, we don't have a product rule yet. Okay? So similar to what we had done with our derivatives before, we write that square root as a rational exponent, t to the 1/2. And now we want to distribute to simplify that expression that we need to find the antiderivative for. That dt, that integrating factor is following us, the integral symbol is following us. All we're doing is working, simplifying that interior. So that notation needs to stay with us. And so as I distribute, we're going to add those exponents. T to 1/2 times t squared, 2 plus 1/2. Get the common denominator. 2 is the same thing as 4/2. So it's going to be 5/2. So t to the 5/2 power plus 3, the coefficient stays. 1 plus 1/2, or 1/2 plus 1. That one might have been quicker. 3/2, right? 1 plus 1/2 is 3/2. And then plus 2 times t to the 1/2. That t to 1/2 stays. And we still have that integrating factor, that dt, right? Just telling us, okay, we're integrating with respect to t, and I forgot to put that t there on that power. There we go, better. So now, as we actually do the antiderivative work over here, 5 halves plus 1, 5 halves plus 2 halves, 7 halves, right? So we're going to get t to the 7 halves, and we're dividing by that same power, 7 halves. When we divide by a fraction, same thing as multiplying by the reciprocal, right? So in this case, this becomes 2/7 t to the 7 halves, and we can rewrite, simplify as we go along, okay? But let's look at this next one. I'm going to keep my plus sign. My 3 sticks around. And now that t to the 3 halves, again, 3 halves plus 1, 3 halves plus 2 halves. We did that earlier. 5 halves, or something similar, I guess, just to say. Okay, so it's plus 3 t to the 5 halves over 5 halves. So when I multiply this through, let me do it, I guess, one more step here. 2/5 t to the 5 halves power. And then lastly, plus 2, 1/2 plus 1, 1/2 plus 2 halves, 3 halves, t to the 3 halves over 3 halves. So this becomes 2 times 2/3 t to the 3 halves power. And now since I don't have any limits of integration, I'm going to attach, don't forget to include this constant of integration. No limits of integration here, an indefinite integral, that constant, that plus c, or whatever symbol you want to use. I'll probably use k. You want to include, okay? And now the bit about simplifying, okay? And so for myself, the power over the root, 2/7. We're taking the square root of t to the 7. Again, we can probably simplify within those as we go. 3 times 2 is 6/5. I don't mind having a improper fraction. The square root t to the 5th. You don't necessarily need that too, but I'll put that there. And then lastly, 2 times 2/3, 4/3. The square root t cubed plus c. And so I don't mind stopping here for that result. If you did want to simplify further, the square root t to the 7th, right, t to the 6th times t to the 1st. That sounds like a t cubed, square root t, plus 6/5 t squared root t, plus 4/3 t root t plus c. Another option, but I'll stop here, okay? But again, that indefinite integral, antiderivative work, that constant integration gets attached anytime there's no limits of integration, okay? I'll stop there. We can work on some more examples from the book and the practice sets. Let me know if you have any questions there.